All right, good. So welcome back. All right, in the third lecture in the series, I'm going to start by telling you about Grover's algorithm, the second most famous quantum algorithm, maybe after Shor's, and tell you about a little bit about some of its applications, what we know about it. And then, with whatever time is left, we'll just have a discussion about, the general classes of quantum algorithms that we don't have time to cover in detail here, including quantum algorithms for machine learning problems. And I'll just explain at a high level, some of what I think are the issues with those algorithms and the sort of the need for further research to sort of pin down, exactly when these algorithms are able to give us a speed up over classical algorithms and when they aren't. Okay, and we'll say something about, some exciting recent results that bear on those questions. I guess both negative results and positive results. Okay, so. Okay, so in the morning we saw Shor's algorithm, Simon's algorithm, right? And these got really, really impressive exponential speedups. I mean, provable exponential speedups in the black box setting. And, and Shor's algorithm, even gives an exponential speedup in the real world under the conjecture that factoring is exponentially hard for a classical computer, which of course we don't know, but some people believe it. Okay, these are exponential speedups, which in some sense is the most that you can hope for from a quantum computer, as we said, at least in terms of gate complexity. Okay, but they were for very, very special, very structured problems, right? And we saw this morning exactly how we had to impose a lot of structure on our oracle F, in order to get the quantum algorithms to work. Okay, so you might say, well, what about like the entire rest of computer science, right? Where typically we don't have that kind of structure. Usually the only, like the only place where you would obviously have all this structure coming from group theory and number theory and so on, maybe is in, applications where you put it there on purpose, such as cryptography. Right, but what about solving NP-complete problems, or just anything that involves searching through a long list? Okay, so let's just consider now the much more general problem of search. Okay, and once again we can formalize the search problem, in this query model. Okay, all we have to do is say, look. You are given black box access to some Boolean function f, in this case from n input bits to 1 output bit. Okay, and let's say your task is to decide whether there's any input x such that f of x equals 1. Okay, or is f just the all zero function, right? So you're just trying to decide if there's a 1, in a string of length n, in other words. Okay, that would be the decision version. Okay, a variant of this question would say, well, let's say, okay, fine, I'll promise you that there is at least 1, 1, in this string, and now your challenge is to find one. Okay, and I might also additionally promise you that the 1 is unique. Okay, but let's leave that to the side for now. Okay, now my first claim, here I even had time to draw an example of the search problem. You see, you got, in this case, it's pretty easy because your brain has parallel processing to interpret everything coming in from your visual system, right, and locate the 1. But you can imagine that if there were 2 to the 100th power entries in this table, that it might be harder. Okay, so so this is this could be a model of the situation that arises anytime you're trying to solve a combinatorial optimization problem or a constraint satisfaction problem, right? You have an enormous space of possible solutions, maybe an astronomically large space. For each one, you know how to evaluate the solution to see does it meet your criteria or not. Right, and now your challenge, is to, just like with the P versus NP problem, right, turn recognition into actual finding of a solution. Okay, so as a first claim, I say that these two variants that I said, the decision version and the search version, are basically equivalent to each other up to low order terms. Okay, that is, if we had an algorithm for one, then we could adapt it to solve the other and vice versa. Does anyone see why? What? Yeah, good. Binary search. So well, I mean, one direction is just trivial, right? If I could find, so by the way, an x such that f of x equals 1, the term for it is a marked item. Okay, we'll just that's the thing that we're trying to find, a marked item. Okay. So in one direction, if we had the ability to find a marked item whenever there is one, then we could just run our finding algorithm, and well, if it finds a marked item, then there was one, and if it doesn't, then there wasn't one, because if there was, it would have found it. Okay. In the other direction, as we just heard, you can use binary search, right? So if we were able to solve the decision problem, then we could just say, well, is there a 1 in the left half of the string? No? Well, okay. Then, is there a 1 in the right half of the string? Right? And wherever there is, then we recurse, and we look in smaller and smaller regions until we would have located the 1. Okay, that will multiply the running time, by at most a logarithmic factor. Right. Okay, so let's start with what is the classical query complexity of this search problem? How many queries would the best classical algorithm need? Anyone? Yeah, well, let's say order n, for, at any rate, right? I mean, it really is as obvious as it looks, right? The best classical algorithm in the world has nothing better to do. Oh, is this it? No. How about this? No. Okay, how about this one? I already tried this one. All right, how about this one? Right? There's really nothing clever to do, okay? So, yes, if I promise you that there is a marked item, then on average you will have found one after at most about n over 2 queries. Okay, but at any rate you're going to need that many. Yeah.
So this n is not the same as the n in
the. It's no. This n is the same as that n. Okay.
It'd be like 2 to the n because
No, because no. I'm sorry. Yeah. You're right. So what I should have. Yeah, you're right. Okay. I made a mistake. What I should have said is, let's say integers from 1 to n. There you go. Thank you. Okay. Appreciate that. Okay. Good. So. All right, so let's say the classical query complexity is of order n. Okay, so now what Grover did is he gave a remarkable quantum algorithm that solves this problem using only order square root of n queries to f. Okay, so and moreover, this algorithm is also efficient in terms of memory and in terms of gate complexity. Okay, so it uses actually only a logarithmic number of qubits, meaning that it doesn't need any workspace. It just needs enough memory to sort of index, an input to f. Okay, and the number of gates is just like square root of n times a logarithmic factor. Okay, so on the one hand, compared to Shor's and Simon's algorithms, this is a much more modest speed up, right? It's merely quadratic as opposed to exponential. Okay. On the other hand, this applies to a much, much broader range of problems, right? I think, just about anything in computer science that you can possibly find has search as some component somewhere. Okay. And so this meant that, like, for 10, 15 years, there was just an endless paper generating algorithm that you could just find any problem and just Groverize some part of it. Okay. And, voila, speed up. Okay, maybe we'll see. And see. No, actually, sometimes it's non-trivial to figure out, where to Groverize. So we'll see a couple examples of that later. Okay. Okay. So let's see how Grover achieves this feat. Okay. So I'm going to start with log of n qubits, all in the 0 state. What do you think I should do first? All right. Yeah. Let's Hadamard. All right, having Hadamarded, what do you think I should do next? Query. Good. This is a quantum algorithm, after all. Okay, now what should I do? Sure, let's Hadamard again. Seems to have worked in other cases. All right, now what next? Well, not yet. I can't measure quite yet, right? This is too early. I could try querying again. And actually, last night when I was preparing, I started wondering, well, what would happen if you just did Hadamard, query F, Hadamard, query F, and you just kept alternating those two things forever. Okay, it took me, 45 minutes to work out the answer. It's kind of interesting, okay, but, long story short, it doesn't work to solve the search problem, okay? And if you want to, understand why it doesn't work and what it does do instead, I will leave that as an enjoyable exercise for you, okay? Well, let me tell you what Grover does that does work, okay? It's slightly different, okay? Only slightly. What we're going to do here is I'm going to put in a matrix, a unitary operation Z, which I'll just define as follows. Okay, so it's just a diagonal unitary operator where it just, flips the amplitude if your string is anything other than the all zero string. Right? And if it's the all zero string, then it does nothing. Okay? So I hope you agree that this would be pretty easy to implement using a quantum circuit. Right? If you don't, then that's another exercise. Okay? Build a little quantum circuit that would implement this unitary on an n-qubit state. Okay, you could also think of it as almost like querying, but in this case querying a fixed black box that always has the all zero string as its marked item, right? Or it's the minus of that. Okay, so I'm going to apply this Z, and then I'm going to go back to the first thing that popped into our heads. I'm just going to Hadamard again, and then I'm going to query F. And then I'm going to Hadamard everything again. And then I'm going to apply that Z again. And so on. And then after I feel that I've done this enough, I'm going to just take all of my qubits and measure them in the computational basis. And I'm going to hope that the marked item X will pop out. Okay? And so the crucial claim that Grover proves is that this is actually going to work, and after a number of iterations of this process that scales only like square root of n. Okay, to be more precise, if we knew that there was just a single marked item, then the exact number of iterations that we would need turns out to be pi over 4 times square root of n. Okay. which, you know, looks mysterious, but we'll see exactly where it comes from. Okay? Okay. So what is going on with this thing? All right, well, as a first step, I want to take the blocks that look like this, right? Hadamards, and then Z, and then Hadamards. And just let me give that its own name. Okay, so the concatenation of, you know, those three blocks, I'm going to call D. And this actually has a name. It's called the Grover diffusion transform. Okay, that's and the question is, well, what is this thing doing? Okay, and the claim is that D simply grabs your quantum state vector, and it takes all of the amplitudes and it inverts each one about whatever is the average of the amplitudes, right? So if your amplitude was 2/3 and the average one was 1/2, well, then your new one is going to be 1/3, right? You just go down. Okay, so. Why does it do that? Well, I could just give that as another exercise. Or, well, we could just say, look, this Z, what is it? Well, it's just like twice 0, 0, yeah, that's right, minus the identity operator. Okay. And this is just twice, let's say, psi minus the identity operator, right? Which, you know, by the irrelevance of global phase, is basically just the identity operator minus twice psi, right? The same difference, where psi is just an equal superposition over all n computational basis states. Okay, and you know, if you think about that enough, well, you know, this is basically just saying, you know, I want to take each amplitude and invert it about the average, right? It's like, all right, yeah, it's an exercise. Okay. So now, so effectively, what we're doing is we are alternating two different types of operations. Namely, queries to F, which sort of invert the amplitude. Oh, and by the way, I should say these are phase queries here. Okay, so queries that just invert flip the amplitude of the marked item or items. Okay, that's the Q of F's, and then in between them, these Grover diffusion transforms. Okay, that invert all amplitudes about the mean amplitude. Okay, and the question is, if you just keep alternating those two things, then what's going to happen? Okay, so it's helpful to draw a picture to get an intuition, right? So we start with an equal superposition over all n possible items, right? So each one initially has amplitude what? 1 over square root of n, right? Okay, now let's say one of them is marked. Okay, let's say this one over here is the marked item. You know, we could give it a dignified name like X star. Okay, so then what's going to happen first? Okay, first I'm going to make a query. What does that do? Yeah, we flip the amplitude of X star. Okay, now that one's minus 1 over square root of n. So far, we don't seem to have accomplished much. Okay, if I now just measure it, right, they're all still going to occur with equal probabilities, right? So now I've got to do something that will boost the amplitude of the marked item, okay? And that is precisely what this diffusion transform is doing, okay? Because let's look at it. What is the average of all these amplitudes? I mean, just roughly. Yeah, it's a little less than 1 over root n. I don't really care how much less. So let's say the average is about there. Okay, so what happens when I invert all of these amplitudes about that average? Huh? Well, each of these guys gets a little bit smaller, right? Because it's, flipped about this line here, right? So these all get just a little bit smaller. But meanwhile, what happens to this one? Right. This one goes all the way up to something of order 3 over square root of n. All right, wow, well, that's something, right? So, if it was good once, then let's do it again. Okay? So now we do another query. What does the query do? Yeah, it just flips this guy again. Makes this minus 3 over square root of n. Okay, and then we again invert about the average. Well, once again, each of these guys gets a little bit smaller. And meanwhile, this one becomes about what? About 5 over square root of n. Yeah. So, wow, we're really, cooking with gas here, right? So, in particular, you can just, just eyeballing it, it looks like, well, I would just have to repeat this, order square root of n times, and a constant fraction, at any rate, of all of my amplitude is going to become concentrated on the marked item, right? If people sometimes ask, like, intuitively, where does the square root of Grover's algorithm come from? Okay, and I think where it comes from is simply, you could say ultimately the Pythagorean theorem, okay, or the fact that amplitudes are square roots of probabilities, if you wish, okay, because if I just imagine a classical randomized algorithm, right, after the first query, I could have found the marked item with what probability? 1 over n. So let's say after 2 queries with probability 2 over n, 3 over n, and so forth. With each query, I can add 1 over n probability mass onto the marked item. Okay, but that means that if I want to get a lot of probability mass on the marked item, then I need order n queries, just as we said before. Just a fancy way of saying that. Okay, but with Grover's algorithm, what we're doing is effectively we're adding order 1 over square root of n amplitude, or actually order 2 over square root of n amplitude onto the marked item with every query that we make. Okay, and this is why we only need order square root of n queries. Okay, you can do a calculation that makes all of that, more rigorous, but let me just show you actually, a different picture of what's going on, a geometric picture that makes it, I think, just like immediately clear, that this is what's happening, and it will even, tell us exactly how long it takes up to that pi over 4 prefactor. All right, so what I'm going to do is I'm going to say, here is our marked item, right? It just, I think of it as just some vector in Hilbert space, right? Here's x star. Okay, now here is my initial state, psi, right, which is just the equal superposition over all n items. Okay, now psi is almost orthogonal to x star, but not quite orthogonal, right? It has an overlap of 1 over square root of n with x star. Okay, so let me also draw the vector in this two-dimensional subspace that is orthogonal to x star. right? I'll give it some name. Let's call it V or something. Okay. And now a key observation is that all of the action in Grover's algorithm is happening within this two-dimensional subspace, right? That is all that's ever going to happen, which means we can fully analyze the algorithm just by, drawing a picture in the plane. Okay, it's never going to leave this subspace. Okay, because let's look at what happens. Well, a query flips the amplitude of x star, right? But what does that do? That's just saying like the vertical component gets flipped. So okay, so like my initial state was here, and now it becomes this, right? The Grover diffusion operator is, well, we just wrote what it is. That one is an inversion about the average, right? Which is just means, like treating psi as my initial state as an axis. I flip about that, right? So after I I take this state and I flip it about psi, well, now it's all the way up here, right? So let's say that my initial angle with the horizontal was theta, right? So then my angle next becomes minus theta, and then I flip about this theta. So now my angle is actually 3 theta. Okay? And then I flip and my angle becomes what? It becomes minus 3 theta first, because I flip about the horizontal. Okay? And then I flip about theta again, and now it becomes what? I hear 6, I hear 5 theta, right? Because, I'm flipping, right, there's a 4 theta distance between this and this. I flip about this, I get 5 theta. Okay? So I get 5 theta, 7 theta, 9 theta, and so forth, right? And all I'm doing is I'm just rotating around this circle at a constant rate. Okay? But theta already was about 1 over square root of n, right? And so, you can see that, well, in order square root of n steps, I'm going to get all the way up to the vertical. Right? There we are. We're done. Okay? And furthermore, well, it's 2 pi radians to go all the way around, right? Well, so it's pi over 2 radians to get here, and I'm doing a 2 theta each time. There's my pi over 4. Okay? So that's Grover's algorithm. Okay? Now, a few questions. What goes on if there was no marked item? Then what happens? What? Yeah, a whole bunch of nothing is what happens. Okay, fine. That's fine. Okay. All right. Here's another question. What if I continue running the algorithm for more than pi over 4 square root of n iterations? Then what's going to happen? Huh? Stay the same? No. What? Yep. The thing is just, look, this is unitary evolution. It doesn't, it don't know when to stop. All right? It's going to just keep going, right? The thing is just going to keep rotating all the way around and around. And so then, ironically, I'm now making my success probability worse and worse as I, with every iteration that I do. Okay? Except then, if I run it even longer, then what's going to happen? Huh? Yep. Yeah, then I go all the way down here, and now my success probability approaches 1 again. Okay, and so on. So if we plot the success probability of Grover's algorithm, meaning let's say of finding the marked item, assuming there's exactly one of them, as a function of the number of iterations, what does it look like? Yes, it is literally a sine wave. Okay. Come on. Wait. Okay. So Running Grover's algorithm has been compared to baking a souffle, and that like you have to take it out of the oven at the right time. If you leave it in for too long, then it starts collapsing. At least so I'm told. I've never baked a souffle, but I'm told that it's like Grover's algorithm. Okay, except that this would be an unusual kind of souffle, whereas you would bake it even longer, then it would rise again, and it would fall again, and so on forever. I don't think that they actually do that. Okay, so but yeah, you do have to let's say make a judicious choice of when to measure. Although if you're a little off, it's not such a big deal, right? Because if I were to measure it like here, let's say, right, there's still a pretty good probability of finding the marked item, even at this point. Okay, on the other hand, if I don't find it, then I got to start over again from the beginning. Yeah.
2 questions.
Yeah.
One, so should I think of this as just Rabi oscillation of a collective spin? And 2,
Sure. If you, yeah.
what happens if there's more than one marked item?
All right, excellent. I was just going to come to that. Okay, so now what? Okay, let me actually throw that back to the audience. What does anyone think would happen if there was more than one marked item? No. All that's going to happen in that case is that these Rabi oscillations, as you have it, will speed up. Okay, the whole thing is just going to happen faster because there's if I have 2 marked items out of n, that is like the same situation as having 1 marked item out of n over 2. Effectively, okay? You can exercise to see why that's the case. Yeah.
What if you don't know how much?
Yeah. All right, good. I'll come to that. Okay. So if there were 2 marked items, then what we'd get would just be this sped up version of the of the same thing. Okay. Okay.
Like the other one,
What?
You find the one and the other, you find the other.
No. We don't know which marked item we're going to find. In fact, at any point, if I find a marked item at all, the one that I find will just be random. Okay, and we know that because the situation is symmetric, right? There's nothing in this algorithm to distinguish one marked item from another one. So therefore, they must all have the same amplitude at every point in time. Okay, so but the speed of the oscillations will depend on the number of marked items. Okay, and in general, if there are k marked items, then the number of iterations that you want to run the thing for will scale like square root of n over k. Okay, this is the formula. Okay, but now we just heard an excellent question, which is, well, what if you don't know k? Right? Well, like in a realistic situation, maybe you don't know how many marked items there are. Okay, but it's still fine. Okay, just relax. Okay, because you could guess. You can just you could start out by guessing that k is n over 2. Let's say that would be pretty aggressively optimistic, you might say. But all right, so maybe you fail. So if you fail, next guess that k is n over 4. Now you got to run it for some more iterations. Okay, if that fails too, now guess that k is n over 8. Guess that it's n over 16, right? Just keep, exponentially decreasing your guess of k until, you get one that's in the right ballpark. Okay? And I claim that in the right ballpark is all you're going to need. Because, once again, if I was a little bit off about the rate, well, I could just pick some random time at which to measure the thing, right? And I'll still have a constant probability of finding the marked item. Okay, not necessarily probability 1, but, even if it's probability half, well, then I just have to repeat the algorithm a constant number of times on average. Okay, so the situation is this. If you know the number of marked items in advance, then Grover's algorithm is exact. Okay, it can be implemented in such a way that it succeeds with 100% probability. Okay, if you don't know the number of marked items in advance, then Grover's algorithm is probabilistic. Right, you can cause it to succeed with like 99.999% probability by just repeating it. What? I don't understand what you're saying. Oh, yeah, right. So there's a little trick for, when you want to have the effect of doing a non-integer number of iterations. That's a good point. There's a trick to achieve that. Okay, I'm omitting that. Okay, but so in general, I'm totally fine with a probabilistic algorithm anyhow. I don't know about you, right? But I'm 99.9999% certainty. It seems greedy to hope for more in this life. Okay, and and even with an unknown number of marked items, Grover will certainly give you that. Question, you?
When you trying to guess the number of marked items,
Yes.
and number 5.
Yeah.
So how do you know? Let's say it's not at number 5, but you first guess it's at number 5. How
Yeah.
do you know whether this fails or not?
Well, if you found a marked item, then you know that you've succeeded. Okay? If you didn't find one, then you try a more conservative guess for the number of marked items, and you try it again. Okay, that's the answer. Yeah.
Is the picture wrong?
What?
You have root N and root A, but here is
Oh, yeah, you're right. Good. Yeah, what I really meant, of course, is that there were 4 marked items here. That's obviously what I meant. All right. Yeah. Other question. Yeah.
Does anything change if you want the problem to be you want to find all of the...
Good question. Yeah, what if you want to find all of the marked items? All right, I'm going to leave that as an exercise for you. Prove that if you want to find all k of the marked items, then the number of steps that you'll need for that is going to be like square root of n times k. Okay? Or, at least show that as an upper bound. To show it as a lower bound is harder. Yeah?
But if you have several marked items and then you will get a superposition of all of them.
Yes, that's right.
You can measure only one.
Well, yeah, I know. Well, that's why it takes more queries, because you're going to have to repeat the thing
Well,
several
then
times.
maybe you will measure the same one.
Yeah, that's possible. Well, you have what's, okay, so that's part of the exercise to deal with that issue, right? It's called the coupon collectors issue, right? Like, you keep buying cereal boxes. Sometimes you're going to see the same prize twice. Okay, but, that's, no, that's what it's called, right? But, but in this case, you could actually do something to avoid that. Like you could, get rid of the prizes that you've already seen, remove them from your sample space. Yeah.
And that's fine if you know K, but
Right.
K, you would never know if you find all of them.
Well, not with absolute certainty you won't. That's true, right. But on the other hand, if you're satisfied with very high probability, then this should work even if you don't know k in advance. Okay? Yeah.
Are these runtimes like the square root of n,
Yeah.
square root of n over k,
Yeah.
known to be lower bounds?
Good question. I was just about to say that as my very next thing. All right. So, now let us ask, could one conceivably give a quantum algorithm that solved the search problem even faster than square root of n? Right? What does anyone think? Well, probably if there was a way, you would have heard about it, right? Okay. So, this... brings us to a fundamental discovery, which is called the BBV Theorem, after Bennett, Bernstein, Broussard, and Vazirani. And I'll just state it as Grover's algorithm is optimal. Okay, if you're just trying to solve the black box search problem, and you have no other information about the structure, of your problem than what is provided by the black box, then any quantum algorithm needs at least order square root of n queries, to find a marked item. Indeed, it needs this many if there are k marked items. Okay, and in fact, even the pi over 4 prefactor is optimal. Was there another question? Yeah.
Yeah, can't you also go faster if you split your set so that you have, like, let's say you split your set in two?
Okay, that's that's an interesting proposal. I invite you to try that and see what happens, right? You can, you could split your set in two, but then, well, now I have to run the algorithm twice, right? And so the advantage I got by having to search a smaller set is actually going to be worse than negated by the fact that, well, now I just have to classically, first search this and then search that. Okay, and I invite you to check that as you split into more and more pieces and did it, then actually the performance will get worse and worse, converging ultimately to the classical algorithm when your pieces were of size 1, right? So indeed, you don't get an advantage that way, unless you could run all of the searches in parallel. But then we're, then we're talking about a different model where you would have parallel, computing. Okay. So yeah.
So this is coming from one of the other lectures where it was stated that Grover's algorithm requires efficient Q-run.
Okay, so there are sort of two settings in which to imagine running Grover's algorithm, right? The first one is for solving a combinatorial optimization problem. Okay, let's say, right? Or let's say where f is just a function that you can compute efficiently for yourself using a small circuit, okay? In that setting, you don't need a QRAM, right? Because, you can just compute f on the fly whenever you need it, okay? On the other hand, in that setting, we certainly can't prove optimality, right? Because that's, in that setting, you could always imagine doing better by going outside of the black box assumption, right? Like certainly if p were equal to np, then, then search would always be easy in that situation, right? Now, the second setting in which to imagine running Grover's algorithm is when your n items are actually laid out in an actual physical database, right? And in that setting, you would need a QRAM to implement it, right? In other words, you would need a huge memory that could store classical bits, but in such a way that they could be accessed in coherent superposition, right? And building that would be a whole additional problem to building a scalable quantum computer, right? Like it's not ruled out by any law of physics that I know. Okay, but you would have to build it, and it looks hard to do. But on the other hand, in that setting, an advantage is that the advantage of Grover's algorithm is then provable, right? Like classically, you just need n time, full stop, and quantumly you could do it with only square root of n. Okay, so all right, so the BBV theorem. Ironically enough, it predates Grover's algorithm. So this is one of the rare algorithms that was proved to be optimal before it was discovered to exist. Okay, I think BBV, when they proved this, they said, all right, well, we really want to show that a quantum computer needs n queries to do search, which is obviously the right answer, but there's some defect of our analysis why we can only show that at least square root of n are needed. Okay. Yeah. Right. So that's the story. This is a beautiful result. If I had another lecture, I could show you like 3 different proofs of this theorem, each one giving different insight, but I don't have time. Okay. So I'm going to sort of leave aside the whole beautiful subject of quantum lower bounds, which is really sort of where I cut my own teeth in grad school. Okay. All right. So now, as I mentioned, there are many, many applications of Grover's algorithm to other problems. Okay. So let's just see just a couple examples to give you the flavor. Let's say that I give you an n-vertex graph, right, via its n by n adjacency matrix. Okay, I just show you where there's an edge and where there's not an edge, and blah blah, right? And I ask you, is this graph connected? That is every vertex reachable from every other one? Right? This is just a classic computer science 101 question. Okay? Does anyone know how do we solve it with, what would be a typical way we would solve it?
Just walk around the graph.
Yeah, walk around the graph. You could do depth first search, right? Or breadth first search, either one, and just see if, your traversal hits every vertex or not. Okay? But this takes, order n squared time in general. Okay? And that is easily seen to be optimal. Why is that optimal in the classical case? Well, here, I'll show you why. Huh? What? What? Huh? Sorry, I didn't hear. Yeah, so let's... All right, something is funny and I still can't hear what it is. But, all right. But, look, imagine that I have this, half and this half. They're both connected. Right now, my whole graph's going to be connected if and only if there is some edge going from somewhere here to somewhere there. Okay, but, there's now just this... giant field, of order n squared entries where I just have to do, brute force search to try to see is there an edge there or not, right? And so, this is just an instance of the search problem from before, but one that's going to take, one that's of size n squared. Okay, so classically, in other words, you clearly basically have to examine, every or almost every entry of your adjacency matrix, if you want to solve this. Okay, by contrast, I claim that there is a quantum algorithm that solves the connectivity problem using only order n, about n to the 3/2 queries. There might be some log factor there. Okay, can anyone see how would we do this quantumly with n to the 3/2? I'll give you a hint. We talked about depth first search. We talked about Grover's algorithm. What happens if you munge them together? Well, huh? Yeah, what we can do, excuse me? Yeah. So basically I can do depth first search, but where each time where I'm looking for sort of a new vertex to add to my tree of the vertices that I've already explored, I use Grover's algorithm to look for one, right? And this will basically take n iterations, each of which will take square root of n steps. Okay, so giving n to the 3/2 overall. Okay, to check that that works in detail. I'll leave that as an exercise. Okay. And there's like 500 other examples of this flavor where you can take some aspect of your algorithm and Groverize it. And that will give you some advantage, which is will either be a quadratic speed up or often less than that, right? It'll be at most quadratic advantage. Okay. Now let me show you one of my personal favorite examples. This one is called the collision problem. Okay. Now here. I'm going to imagine that we have black box access to a function f, mapping the integers from 1 to n to themselves. Let's say n is even. And let's say I promise you that f is a 2-to-1 function. Okay? So, every output of f has exactly 2 preimages. And your problem is simply to find any collision. Okay, that is, find any x and y such that f of x equals f of y. Okay. So this models a lot of problems that you might care about. And so but one thing it models is breaking what are called collision-resistant hash functions in cryptography, which are which power a lot of modern cryptography, but which, as their name suggests, are designed to make it hard to find collisions, right? So because if you find a collision, then you break the thing. Okay, so let's first look classically. What is the classical query complexity of the collision problem? Anyone? What? Square root of n. How come? Yeah, birthday paradox. Yeah, it's exactly the same situation as we saw with Simon's problem, right? With Simon's problem, there was additional structure, but the classical algorithm was sort of unable to exploit it, right? And so, it's square root of n queries until by the birthday paradox, you're likely to have found a collision, okay? And that can easily be seen to be optimal. Okay. Now, what about the quantum case? Well, we're kind of in a funny situation, right? And that we could almost solve this thing with only one query to f. Okay? How? Well, let's just repeat the same strategy that worked for Simon's problem and for period finding. Let's just make a superposition, equal superposition over all inputs x. Let's then compute f of x in superposition, or evaluate it. Let's then just discard this register, and then what's going to be left over here? Yeah, x plus y over square root of 2 for some collision pair x and y, right? Now, if only we could measure this thing twice, we'd be done. Okay, right? It's so frustrating. It's like we've got it right almost in our grasp. Okay, but the trouble is you measure this and you only see one of the two. Right, you see x or y. And furthermore, unlike with Simon's problem, here we don't know how x and y are related to each other, right? There's no kind of global promise about it. And so if we try to do, the Hadamard's, our trusted tool, or the Fourier transform or whatever, we'll find that it doesn't work. Okay, so we're in this sort of fringe intermediate situation where our problem has more structure to it than the Grover problem, than the search problem, right? Because, being 2 to 1 is this very global property of our function, right? And there are many, many collisions to be found. Okay, but there's also less structure than there was in Simon's or Shor's problem. Right? So now it's like we're zooming in and we're saying, okay, it's like Rumpelstiltskin. Okay, quantum could do period finding. Well, can it do this? Okay, so now we come to a beautiful observation of Broussard, Hoyer, and Tapp from 1997. Okay? And that what they say is that, let's just sort of munge together Grover's algorithm, right? So, we could certainly use Grover's algorithm to find a collision in square root of n time, right? How do we do it? We'll just look for something that collides with the very first item, with f of 1, for example, right? So that would give us square root of n. Okay, and then we also have square root of n from a completely different source coming from the classical birthday attack. Right? So let's munge the two together somehow and see what happens. And what happens, it sounds like a joke, okay, but it's the truth. You combine these two different square root of n's and you get a cube root of n algorithm. Okay? So how does this work? All right, well, here's how to do it. So in the first phase, we're going to just pick cube root of n random x values classically, and we're just going to query them. Okay, so we've got like I should have drawn this bigger. F of x1, f of x2, and so forth for some randomly chosen x1 up to x cube root of n. Okay, and now I'll just store all of these in some lookup table. Maybe I'll sort them for fast lookup, although that won't affect the query complexity. Okay, now in the second phase, I'm going to pick n to the 2/3 other inputs. Let's call them, y1, y2, up to yn to the 2/3. And now I'm going to do a Grover search over these things. Okay, but what will my Grover search do? Well, for each yi, we're going to count it as a marked item if and only if what? Anyone? Yes, we're going to count each one as marked if and only if it collides with one of these cube root of n items that we queried in the first phase. Okay, and and that doesn't require any additional queries to check that. Okay. So what is the total running time of this algorithm? Huh? Okay, I can't, you have to speak louder. Can't hear. Yeah. Okay, right. So the first classical phase took cube root of n time. The Grover phase took square root of n to the 2/3 time, so overall it's cube root of n, right? And we just chose these parameters to balance the two things out. Okay, so fine. So we can get Grover's algorithm can give us some quantum advantage for finding a collision, right? Not quite a quadratic advantage, but instead of square root of n, we get cube root of n. Okay, so now it was, you might wonder, could we do better than that, right? So the sort of, I guess the best known thing that I did in grad school was to prove the first lower bound on the quantum query complexity of this problem of collision finding. So the result that I was able to get is that any quantum algorithm for finding collisions needs at least order n to the 1/5 queries. Okay. Now you may say, well, that's not quite satisfactory because it doesn't match this. Well, it took me like 4 months of the hardest work I ever did in my life to get the 1/5. So, take it or leave it. Okay, but fortunately, just within a month after I did this, Yaoyan Shi was able to improve it, and with a more refined analysis, he was able to get that actually you need at least n to the 1/3 queries, so it matches it matches Broussard-Hoyer and Tapp's upper bound. Okay, this had the strange situation, that sort of before this, I think that you could prove that at least 2 queries were needed. Okay, but at any rate, we had no lower bound that even grew as a function of n. Okay, that was how bad it was. Gesundheit. Okay. What? Oh, all right. Well, you're asking for the implementation details of this thing? How you do it as a quantum circuit?
Yes, there's like one cube number of f(x).
Yeah. Oh, right, but see, again, we're in the world of query complexity, right? We've already queried those things. Okay, so just looking them up in your own lookup table, that does not count as an additional query to f. Okay, but furthermore, if you like, you can even make the computational complexity small by just sorting the things, right? Or putting them in a binary search tree, right? You can pre-process them to make it faster. Okay. A good question. Okay, but like when we define query complexity, we mention that sometimes you need these workspace qubits, right? Which seem kind of strange. Okay, this is this is an example where where a workspace is actually needed, in quantum query complexity, as far as anybody knows, right? So here's an open problem. Okay, no one to this day knows whether you can find collisions using both, let's say, cube root of n quantum queries and, let's say, a small number of qubits, like, let's say, log of n qubits. For that matter, anything less than cube root of n. Okay. So as far as we know, a workspace is needed. Although in this case, it's only a classical workspace. Whereas for other quantum algorithms that I won't have time to show you, you actually need a quantum, a superposed workspace. Questions? Okay. All right. So now let me just list in my remaining half hour. Let me. One other thing that I wanted to mention, because we talked before about oracle separations between complexity classes, right? A corollary of the BBV theorem is that there exists an oracle A relative to which NP is not contained in BQP, right? Like, this is just like another way of stating the content of the BBV theorem, that Grover's algorithm is optimal, right? It's saying that relative to an oracle, that there are NP problems that will take exponential time to solve even using a quantum computer. Okay, so we, as I told you, we don't know the relationship between NP and BQP in the real world. Most of us believe that NP is not in BQP, so like that quantum computers cannot solve NP complete problems in polynomial time, or that, in the worst case, you'll at most get like a quadratic, a Grover type of speed up. Okay, but what can be shown is that at any rate that is true in some oracle world. Okay, good. Okay, so. So what are the families of quantum algorithms that I haven't had time to talk about in these lectures? Well, first of all, there's quantum simulation, right? Just algorithms to simulate quantum physics and chemistry, right? You can call that what a quantum computer just does in its sleep, except that actually sometimes it's very non-trivial to figure out how to take your system with its bosons, its fermions, its Hamiltonians, and so on, and actually map it onto a quantum computer with a discrete set of gates acting on qubits, right? But there's been a lot of work on that problem, including, a lot of breakthrough results on it just within the last few years on the complexity of Hamiltonian simulation. Okay, so that's a whole story that I haven't gone into. But this, I think, if and when we have practical quantum computers, this might be the most useful thing that you can do with them. Right? It's sort of, maybe it's gotten, historically got less attention than it deserved. Just, but this was also like Feynman's original application that he had in mind. Yeah. Okay. Then there's, I haven't said anything about quantum supremacy experiments, right? It's not clear whether to even count those as algorithms, right? Because, all they're trying to do is do something that is hard to simulate with a classical computer, right? They're not trying to get any particular right answer, just be hard to simulate, okay? And thereby, disprove the skeptics of quantum computing. Okay, but actually, it's emerged very recently that even these quantum supremacy experiments could have some applications. In particular, one could use them, for example, to generate cryptographically secure random bits, which could then be used for cryptocurrencies and for other applications. Okay, that's some forthcoming work, but that's a whole other story that I won't have time to go into. Okay, there's a whole class of beautiful quantum algorithms that are based on taking quantum walks on graphs. Okay, so I think we mentioned in passing Ambianus's element distinctness algorithm. That's a famous algorithm in this category. There's something called the Childs et al. Glued trees algorithm. And that one's notable because it solves a very contrived problem, but it does it exponentially faster than you could do it classically. Provably so in the black box model, right? And so that's a completely different exponential quantum speed up than the ones arising from, Shor's and Simon's algorithms, right? Or the quantum Fourier transform, right? So far it hasn't found any real applications, but, it deserves to, okay? I hope it does because it's a really striking thing. Okay, so there's quantum walk algorithms. More typically, what these would give you is like Grover or sub-Grover style speed-ups. Okay, but also in situations where Grover's algorithm by itself does not work. Sometimes these quantum walk algorithms work, or they give you a somewhat better running time. All right, what else we got? Yeah, so there's, the adiabatic algorithm. There's, the new thing that Farhi and his friends talk about that they call QAOA. And there's this whole other class of what I'll call quantum heuristic algorithms. Okay, so you already learned about these, I gather, from Matthias Treuer's lectures. So he told you all about them. So I won't, say much about it, but, long story short, these are heuristic algorithms in the sense that there is almost never a theoretical analysis that sort of shows you that it's going to get a speed up over classical, right, when you compare them head to head. What there is, more commonly, is that, well, you can't rule out that there's not a speed up. Or at least, we can't. And so when we start getting, decent-sized quantum computers, people are going to try these things out, and they're going to see how well they do, right? And so then that's a whole sort of different mode of computer science, right? That's the empirical mode. Okay, my guess is that these algorithms will have some, some uses or some situations where they do well, but if you're looking for, let's say, exponential speed up, so let's say like way more than Grover's algorithm, I think the case that these are going to give them to you in many in a wide range of practical situations is not a strong one. Okay, that's my personal opinion. Yeah.
Is it also true for the QLA? Because I thought
Yeah.
there was some complexity.
Yeah, well, right. Well, so the complexity result that they have is basically just that you can use QAOA to run a quantum supremacy experiment. Okay, so this is you're talking about a paper of Harrow and Farhi, and basically what they say is, well, look, we can't. Initially they were hoping to prove that the QAOA solves a useful problem, that we don't know how to solve classically, right? Or let's say gets a better approximation ratio for some NP-hard optimization problem than we know how to get classically, right? For a while they thought they could do this, and then I wrote a blog post about it, and then that caused a bunch of classical computer scientists to say, no, we can match and even improve that performance with a classical algorithm, now that you tell us that you care about this question. Okay, so then what they did is they sort of stepped back, and in the paper you mentioned, they say, okay, fine, But, the QAOA's pattern of failures is one that you won't be able to reproduce with a classical computer. Okay, right? There won't be a classical algorithm to sample the same distribution over wrong answers as it samples from unless the polynomial hierarchy collapses. So the same style of result that we had for boson sampling and so forth, right? I think, one of the best science cartoons I ever saw involves, like an alchemist who's like, wearing his pointy hat, and he's all dejected, and he's saying to his apprentice, at this point, I would be thrilled if I could even transmute gold into lead. Okay, so I find in theoretical computer science, that cartoon applies to half of what we do. Okay, so okay. Yeah, and then there is this HHL algorithm after Harrow, Hasidim, and Lloyd, which they discovered a decade ago, which is billed as sort of solving systems of linear equations exponentially faster than you could do it classically, although there are a bunch of caveats to that statement that are extremely important and that we'll say something about. Okay, and HHL sort of started a gold rush of attempts, let's say, to find quantum algorithms for machine learning problems. Okay, and this has become a whole field in itself, of quantum machine learning. Okay, now my personal opinion is that the field of quantum machine learning is a mess right now. Okay, and that is a positive statement, right? That means if you're looking for something to do, you should go into things that that are messes. Okay, we don't understand what's going on, and it is very plausible that with some more research we will understand more. Okay, so here's what I see. Okay, so there's been a flurry of papers over the last decade which have proposed quantum algorithms for what? For k-means clustering, for support vector machines, estimating Betty numbers. Now there's even people doing quantum deep learning, which is which I think is even more of a mess, let's say. Typically, and often, when you read the papers, they will claim that that these algorithms get exponential speedups. Right, and if you read the original paper, then you'll see all the asterisks, on that statement. But then when people repeat it, then they forget the asterisks. Okay, so here's what I see as sort of typically, the main issue that these algorithms face. Okay, so typically, they're doing some sort of high-dimensional linear algebra, right? Which indeed is what much of machine learning consists of. Right, that's what it is, right? And so you might say that sounds like a perfect match for quantum computing, because quantum mechanics is high-dimensional linear algebra too, right? Match made in heaven. Okay, typically what will happen? Okay, so let's take the example of the HHL algorithm, right? So the problem being addressed is that you have, a system of linear equations, ax equals b, you want to solve for x, right? And classically, of course, this takes well, let's say matrix multiplication time, or in practice n cubed time to solve it, if A is a dense matrix. And HHL give a quantum algorithm that in some sense could be claimed to solve this problem in logarithmic time. Okay, but what is that sense? All right, well, first of all, they're going to assume that you are given or are able to prepare the vector B as a quantum state. Okay? So you need to be able to make a quantum state whose amplitudes are a normalized version of the vector B. All right? Fine. And then, but sort of it gets worse, right? Because, if now for the algorithm to work, we need some assumptions on the matrix A. In particular, A has to be well conditioned. All right, that's not, we won't worry too much about that. That's reasonable. But also you have to be able to sort of efficiently apply a Hamiltonian corresponding to A. Right? And then, okay, that puts a lot of further constraints. Okay, like if A is a sparse matrix and you know where its non-zero entries are, then yeah, you could do that. Right? This has been shown. Okay, and there are some other cases, some other classes of matrices for which that would be a reasonable assumption, but you got to be able to apply that Hamiltonian. Right? So that's a big assumption. Okay, but let's say that that's satisfied. Okay? Then, here's the kicker. Okay, the thing that you get out at the end of this algorithm, your solution vector will not be written down anywhere you can see. Okay, it will be just the list of amplitudes of another quantum state. Okay, another superposition. Okay, and now what HHL will say to you in effect is, well, our work is done. Here you go, okay? All right, now, you actually wanted to know something about X? All right, well then, and then you go, you design a measurement that tells you something about this X, okay? Now, I don't want to be too dismissive because it's quite possible that, there are situations where you could do all of this, right? But what you need to, in order for the algorithm to be useful, what you need to find is, so to speak, an end-to-end application for it, right? That is, you need to find some real-world problem where you start with classical input, and then you use HHL somewhere in the middle, and then you end up, let's say you only need to know some, rough, information about X that you could get by measuring that state, and then that would give you a classical output. Okay. But then even that is not enough, because now, now that you've found this end-to-end application, now you need to step back and say, well, if that's all I wanted was this mapping from classical input to classical output that HHL is able to give me, now I need to convince myself that there was not also a fast classical algorithm that would give me that. Okay? So if you meet all of those requirements, then it is possible that HHL could give you a real-world exponential speedup. Okay, but you could say that in effect, like what has been done is to sort of give the analog of like the quantum Fourier transform inside of Shor's algorithm, right? But not all of the surrounding stuff that makes Shor's algorithm do something useful in the real world, or at least nefariously useful, breaking RSA, right? So so it's the surrounding stuff that sort of has to be supplied. And I think this is a very exciting area for research, particularly for students, looking for messes to clean up, right? Understand, what are the end-to-end applications of these quantum machine learning algorithms, and do they actually lead to real speed-ups over the best classical algorithms that we could design for those same applications? Okay, so what is the status of looking for those end-to-end applications of quantum machine learning? Well, there's one really striking sort of flagship example of a success in finding such an application, or rather, there was until this week. Okay. Okay, so a couple of years ago, Karanidis and Prakash wrote a beautiful paper in which they proposed a quantum algorithm for a problem involving recommendation systems. Okay, so the problem is quite complicated to formally define. Okay, but I can give you the flavor of it. Okay, so this is sort of an abstraction of the problem that is faced by Netflix, for example, or by Amazon. You know, when they say, like, you know, customers who bought this product may also like this one, you know, and they try to recommend to you things that, you know, you might want to buy, right? What is going on under the hood there? Okay, well, basically, you imagine there's some M by N preference matrix, right? We imagine, you know, we've got M users and we have N products, right, that we're selling. And we have some very sparse data about which users like or dislike which products, right? So, like, we have, you know, we filled in just like a very few entries of this matrix, right, by, you know, the feedback we've gotten from the users or whatever. Okay, and now and we'll also assume that this sparse data that we do have is conveniently organized into like a binary search tree data structure so that it can be looked up quickly. Okay, and now we make an assumption that this matrix, the full preference matrix, if we knew it, would be close to a matrix of low rank. Right? Why do you assume that? Well, empirically, it turns out often enough to be true. Okay, and basically what it's saying is that there's not too many, you know, ways that the users differ in their preferences, right? Like, there's kind of like the amount that you like romantic comedies, or, you know, there's the, like, you know, amount, you know, whatever, right? But, you know, there's like, it's not like your liking of every movie is totally uncorrelated with your liking of every other movie, right? There's sort of a limited number of dimensions in which people vary in their movie, for the most part, in their movie preferences. Okay, so that's the low rank assumption. And now what the Karanides-Prakash algorithm did is that it is able to sample from the distribution over, you know, recommendation. So sample from a distribution over products that a given user is likely to want, you know, in this model, in time, which is polynomial in log n, log m, k, which is the rank of the preference matrix, and the inverses of some other error parameters that show up. Okay? But basically, you know, it is polylogarithmic time. Okay, you should think of, right? Polylog in the size of the matrix. And so that was an exponential improvement over the best that anyone knew how to do classically, right? Classically, it seemed you were just stuck doing linear algebra on this entire m by n matrix. Right? And if you're going to do that, well, then of course it's going to take, you know, at least like m times n steps, right? Because you've got to read in the whole matrix. Okay? You know, the key, you know, so Karanides and Prakash were not able to sort of compute singular values of this matrix or, you know, anything like that. You know, all their algorithm does is it samples, you know, products for a given user. But, you know, but they said that's okay because that's all you want in the end anyway for this application, right? So, you know, so that was a very, very insightful observation that they made. Okay, so, you know, but now, you know, what was not clear, you know, was, well, is this actually an exponential speed up, right? And, you know, you know, this seems like kind of just a nerdy question for some, you know, complexity theorists to worry about while the, you know, practical people forge ahead, right, and discover more algorithms, right? You know, yeah, it would be nice to rule out that there's a fast classical algorithm to solve the same problem, but, you know, really that's just a matter of dotting some I's and crossing some T's, right? But nevertheless, you know, I felt that quantum machine learning, you know, should aspire to the same standard of rigor that we had, let's say, for Simon's algorithm and Grover's algorithm and Shor's algorithm, where we really try to understand well, what separation are we getting? Can we actually prove lower bounds in the black box model that show us that our quantum algorithm is doing something faster? Okay, so I gave this problem to an undergrad, okay, named Ewin Tang, to just rule out a fast classical algorithm, okay? Ewin spent a year on it, was unable to rule out such a fast classical algorithm, but later eventually discovered a reason for that, which is that there is a fast classical algorithm for this problem, okay? And that is what is in the preprint that, Ewin just put out and that I blogged about a couple days ago, okay? In fact, this KP algorithm, does not get an exponential speed up over the best that you could do classically. It at most gets a power of 1 over 33 speed up. Okay, so there is a classical randomized algorithm to do the same task whose running time is at most the running time of the quantum algorithm to the 33rd power. Okay. Now, it sounds comical, but I am certain that that's far from tight, and that furthermore, that the algorithm would be much better in practice than it could be guaranteed to be in theory. Okay. So, but there's a lot of room here for trying to understand what is going on. Are there other cases where we could actually just prove, an exponential separation in the black box model, and then it would be real, right? And then we would know for sure that no Ewin Tang is going to come along and refute it later. Again, at least in the black box model. Yeah. Mm-hmm. Mm-hmm. Yeah. Yeah. Well, okay. So in the case of deep learning, I completely agree. Right. The theory. Well, actually, you could say even there's an opportunity, right? But the theory of deep learning is sort of in an abysmal state, compared to what people are able to do in practice. Which again, you could see as an opportunity, but you could say until we even, have any understanding classically, surely it's premature to think about the quantum case. Okay. But for a lot of these other problems, right? Like right here, does the KP algorithm get an exponential speed up? That was a very well-defined theoretical question, and it has now been answered, right? And I expect that there will be more questions like that are amenable to theoretical analysis. Okay, and hopefully some positive results too. Okay, so if I have a few minutes to just mention one last thing, because I wanted to end on a more positive note, and not be such a downer. Well, this is not a total downer because now, we have a classical algorithm that, who knows, maybe it'll make Netflix some money, right? And, and you could implement it, you could run it, right? You should get down that 33rd power first, okay? But it's a classical algorithm that was only discovered by looking at a quantum algorithm, right? And it's actually far from the only example of that we now have. Right, so quantum computing has spin-offs in the classical world. Okay. Mm-hmm. All right, so I just wanted to mention. A problem that I defined in 2009 called correlation, which actually can be used to get an exponential quantum speed up for a quote-unquote machine learning problem. It's just not a problem that I know that anyone cares about. Okay. So in the correlation problem, you're given black box access to two Boolean functions, f and g, both of which map n bits to, let's say, 1s and -1s. Okay? And your task is to estimate a quantity that I will call phi of f comma g, which is defined as some normalizing factor times the sum over all n-bit strings x and y of f of x minus 1 to the x dot y times g of y. Okay? This will always be between 1 and minus 1, this quantity, right? So let's say estimate it to within epsilon. Like, is it close to 0? As it would be if f and g were just two random Boolean functions, totally uncorrelated with each other. Or, like, is it, large, like as it would be if g was close to the Boolean Fourier transform of f. Okay, hence, correlation with Fourier transform, hence correlation. Okay, so can anyone sort of see a quantum algorithm to solve this problem quickly? Well, it's not, I sort of designed the problem around the quantum algorithm that solves it. So you just have to work backwards to what, well, we can use the favorite, let's start with n qubits in the 0 state. What should we do next? Hadamard. Okay, what next? Let's query one of the functions. How about f? What next? Let's do Hadamard again. Another round of Hadamards. Never hurt anyone. Okay? Now let's query g. And now let's just do one more round of Hadamards. And now let's measure. Okay? Now, exercise for you. Show that the amplitude with which this circuit returns the all 0 state is precisely the correlation phi of f comma g, right? So just by seeing how likely it is that this algorithm gives you back the all 0 state, you tell whether f and g are correlated or they're not. Okay, by contrast, Andras Ambayanis and I, in 2015, were able to show that any classical algorithm for estimating correlation requires at least 2 to the n over 2 divided by n queries. Okay, which we also know that 2 to the n over 2 suffices. So this is roughly the right answer. Yeah.
You said that so as to measure 0.
Mm-hmm. The probability is going to be the square of that.
Then I need to measure enough time to estimate.
Well, yeah, of course. I mean, like if you wanted to within epsilon, then let's say 1 over epsilon squared times. Okay? All right? So, yeah, measure enough times to get a good enough estimate, of course. Okay? So, so this does, this is yet another sort of provable enormous quantum speed up in query complexity. Okay, but it's more than that, because as some of you may have heard, there was a breakthrough in complexity theory just a couple of months ago, when Ron Raz and Avishai Tal, solving a 25-year-old open problem, have now shown, that there exists an oracle A relative to which BQP is not contained in the entire polynomial hierarchy, which is a generalization of NP to allow with like NP with an NP oracle, NP with an NP oracle with an NP oracle, and so forth. Okay? Even that entire stack of NPs still cannot do everything a quantum computer can do. That is what they show. And this is actually why I introduced the correlation problem, because I was trying to prove this. So I couldn't show that correlation was not in pH, but that's what Raz and Tal have now done. They use the correlation problem. They actually, they use a slight variant of it, where you just want to know, you need to know whether the correlation is like 0 or 1 over n. Okay? And for that, they're able to show that that problem, as a black box problem, is in BQP, but is not is solvable in pH. Okay, so that was a major achievement. Okay, but now, I continue to, I have a soft spot for the speculation that correlation might be good for something, okay, in the real world. In particular, like, let's say I had some, collection of enormous vectors stored in some memory somewhere, and I wanted to cluster together similar vectors, right? But let's say, for some of the vectors, I don't know which ones, accidentally I give not the vector itself, but the Fourier transform of the vector. Why? I don't know. Okay? But, now I've got kind of a classically, maybe challenging clustering problem, because I need to at least read in the entire vectors and do FFTs on them, right, probably, in order to solve this. But correlation could come to the rescue. So there you have it. There would be an exponential quantum speedup for some machine learning problem. But but I hope but sort of you're going to have, just like with every other quantum algorithm, you're going to have to exploit minus signs. You're going to have to choreograph patterns of interference and actually use the hammer that quantum mechanics gives you. Right? This is just one way to do it, but however you could do it for quantum machine learning or for any other application, sort of that is what has to be going on somewhere inside your quantum algorithm. All right, so let me stop. So thanks.